Okay, so today we're going to start the new chapter called Sketching Functions. You may also see this as curve sketching. So what we're going to do is use calculus to figure out how to sketch pretty complicated looking functions. So you should already be familiar with sketching lines, parabolas, cubics, and so on. So we're going to start off with something like that, and then move on to something called rational functions, which is a bit more complicated, but we'll see what we're going to do. Okay, so the first thing that we look out for with this curve sketching is particular features of the function that will allow us to complete the sketch. Okay, so we look for particular features of the function to aid in the sketching. Okay, so this is a list of things that we can calculate. Once we have this list, it's pretty much connect the dots, and then we can see what the function looks like. Okay, so let's see what this list is. So number one, x-intercepts. So this is very familiar from what you did in high school. Okay, then we have y-intercepts. Okay, number three, intervals of increase and decrease. So we're looking for values of x where the function is increasing, values of x where the function is decreasing. Number four, so in between these two intervals, so if it's increasing then decreasing, we know that it's a maximum. If it's decreasing then increasing, we know it's a minimum. And to generalize that, we say turning points. Okay, so we see, does this function have any turning points? We're going to use that to sketch the curves. Number four, points of inflection. So if you haven't heard that before, we'll go through it. Okay, and number five, vertical and horizontal asymptotes. So just for your information, before we get into the calculations, for tests and assessments and so on, most of the marks will be going into calculating these. Okay, so it will be few marks that will be for the actual sketch. Most of it will be for these calculations. Okay. Okay, so with this list of 5 things, we can use that to get an idea of what this function should look like. Okay, once we plot all these things, we just connect the dots, and then we get an idea of what it looks like. So it won't be very accurate, but we get a rough idea of where the function reaches a maximum, where it's decreasing, and so on. Okay, so it's a rough idea of what this function will look like. Okay, so these are just 5 of the basic things that we'll use. There might be more that we'll use, there might be less than this that we'll use, but if you can remember these 5, then that should be enough to answer the questions. Okay, so sometimes there's more, sometimes there's less, but most of the times this list of 5 things will suffice. Okay, so let's look at an example. Okay, so that's the best way to practice these, is to do examples. Just looking at the notes is not going to help you with sketching. Okay, it's a very practical thing. So you have to do these examples, practice your sketching, and then you'll get better with it. Okay, so number 1, we have y is equal to x cubed plus x. Okay, so in high school you would have done sketching parabolas, so that's fairly easy. Here we're moving a little bit up to cubics. Okay, so it's a little bit more difficult than parabolas, but not so much. Okay, so we just go through that list. We look for the x-intercepts, the y-intercepts, intervals of increase, decrease, turning points, and asymptotes. Now here, it's just a polynomial, so we know there's not going to be any asymptotes. We don't need to worry about that. Later on, we'll see if we're dividing by something that could be 0, then we're going to get some asymptotes, but here we don't need to worry. Okay, so we can remove that from the list. So let's start with the x-intercepts. Okay, so x-intercepts. We know that if we're trying to find the x-intercepts, we should let y be 0. Okay, please make sure that's the first line you write down so you don't mix up what you're letting be 0. So if you want to find the x-intercepts, you let y be 0. If you want to find the y-intercept, you let x be 0. Please don't mix that up. Okay, so we let y be 0, and then we write the rest. So x cubed plus x. Now, just as a little bit of advice or warning, however you want to take it, please make sure that you go over your factoring. So factoring of quadratics and factoring of cubics. It is very important that you know how to do that. For a lot of these questions with polynomials and rational functions, there's a lot of factoring to get the answer. Okay, if you don't know how to factor, you won't be able to complete this list of things, and then you won't be able to sketch it. You see, that's quite a lot of stuff that you're leaving out. Okay, so please, very, very important. If you need to go over your quadratic and cubic factoring, please do so. Okay, it's a very key tool that we use when calculating these. Okay, so if you don't know how to factor, you won't even get to the part with sketching. Okay, so please make sure you go over that. So here it's pretty simple. We can just take out an x, and then we have x squared plus 1. And then we need to look at this for a bit and see what kind of values we get. So we see that this x, that could be 0. So if the x is 0, then everything's fine. So that's one of the solutions. If we look at this other bracket, x squared plus 1, that can't be 0. Right? X squared plus 1 is always positive, so that term doesn't give us anything. Okay, so just remember, if we have something like a times b is 0, either a is 0 or b is 0. In this case, the second term can't be 0, so it's only this first one. Please do not look at the second term here and try and solve for x. Okay, it's not going to work. So we only have one solution, so we have one x-intercept. If you try and find this other one, it's not going to work, you're going to get it wrong. So we have one solution, x is 0, y is 0, by assumption there. So we have one x-intercept. Okay. So what's nice to do is, as we find these points, just make a list of them so that when you do the final sketch, you can just plot the points and then join up the lines. Okay, so we don't want to forget any points along the way. Okay, so that's the first point. Next, we can find the y-intercepts. So y-intercepts, that means we let x be 0, and we'll see what we get. So here, if we let x be 0, we just get 0 plus 0, that's 0, so y equals 0. And we get 0, 0. Okay, which is the same as what we got before. So the x-intercept is the same as the y-intercept, which means it passes both of the axes through the origin. Okay, so when we're sketching this, we need to think to ourselves, this function must pass through the origin. Okay, so just something to think about while you're doing this. The function must pass through the origin. So when you're sketching it and you see that you're not going through the origin, go back and see what you've done wrong. Okay, so just make a note here, the function must pass through the origin. So we can check that later. When we look at our sketch, we can see that it should go through the origin. Okay, so that's the first two things done. We've got the x-intercepts, we've got the y-intercepts. Now we need to look for the intervals of increase and decrease. So where's the function going up? Where's the function going down? So intervals of increase and decrease. And we'll see that once we have these intervals, we can find the turning points pretty easily from that. So we know that intervals of increase and decrease is equivalent to finding where the gradient is positive or negative. So we need to find y prime. That's going to be 3x squared plus 1. If we look back here, so take the 3 down, 3x squared plus 1. Okay, again, please make sure you go over your derivatives. So when we're finding intervals of increase and decrease and inflection points, we need to take first derivatives and second derivatives. If you need to go over your derivatives, please do that as well. Okay, so we're going to set this equal to 0, like we had before with the finding the maximum and the minimum. So here we have 3x squared plus 1 equals 0. Just looking at this for a little bit, we see that there's no solution to this. Right? If we look on the left-hand side, that is always going to be something positive. Right? It's never going to be 0. So in fact, there's no solution for this. No solution for the turning points. And also, from what I said, the left-hand side there, so this bit over here, is always positive. So that means the gradient is always positive, which means the function is always increasing. So no solution for turning points. That's the first thing we notice. The second thing we notice is that the gradient is always positive. And what does it mean for the gradient to be always positive? It means that it's always increasing. Okay, so we write that down just to keep it there, so when we're sketching, we know what to do. Okay, so since there's no turning points and it's always increasing, the next thing we should look at is inflection points. So if you're not familiar with what an inflection point is, or if you forgot from high school, an inflection point is where the concavity of the function changes. So just as a little example here, okay, we see that in this first little portion, so let's say this pink part, we see that it's a cup shape facing upwards. Okay, so we say that's concave up. The second derivative will be positive, or we say it's concave up. For the next portion, this portion here in green, we see that it's like a cup shape but facing down. We say it's concave down, or the second derivative is negative. Okay, that is how we find the inflection point. It's the point in the middle here where it changes concavity. So it goes from being concave up to being concave down, or it goes from being concave down to concave up. Wherever there's that change, we call that an inflection point. Okay, so since there's no turning points to find, the next thing we look for is these inflection points. Okay, so we look for inflection points. Okay, so like I said at the beginning, that list of 5 things, you may need more than those 5, you may need less than those 5. In this case, we didn't need to look for asymptotes, but we do need to look for inflection points. Okay, so here we look for the second derivative. So y double prime, that's going to be equal to 6x. We set that equal to 0, same as we do for finding the turning points. Inflection points, same idea. So here we have an inflection point at x equals 0. Okay, so that's where it changes from one concavity to another. But what does it change from? What does it change to? Well, we see that this y double prime, that's the concavity, is equal to 6x. So if x is less than 0, this double derivative will be negative, so it will be concave down. So when x is less than 0, y double prime is also less than 0, which means it's concave down. If x is greater than 0, then y double prime is also greater than 0, and that means it's concave up. Okay, so we see that around this origin point, it flips from being pointing down to then pointing up. But remember, along the whole way, it's increasing. So we need to keep all of that in mind when we're sketching this. So let's do that. We draw in our axes. So this doesn't have to be to scale, but then please make sure that it's labeled. Okay, so it can be squashed vertically or horizontally, but if you're going to do that, make sure all your points are labeled. If you're going to make it to scale, then make sure that your axes are labeled, so I can see where those points are. Okay, so we had one point of interest, that was the origin, so let's label that. And we know that it's always increasing, so from the bottom left to the top right, the function's going to go up and up and up. And we also know when x is less than 0, it's concave down, so it must be like a cup shape pointing down. After x equals 0, it's concave up, so it must be going up. Okay, so with all that in mind, what is this going to look like? So for the left side, where it's concave down and increasing, it must look like this. Right? That's concave down because we see it's part of a cup shape, but pointing down. It's also increasing. We see that at every point, the function's getting bigger going there. And it's going through the origin like we said. So that part's sorted out. What about the other side? It's increasing. Yeah, you got it? Yeah. It's increasing and it's concave up. So it must look like this. If you want to draw the arrows to show increasing or decreasing, you can do that. That's perfectly fine. Okay, so that's everything we need to label. We've labeled the inflection points and the intercept there, so that's fine. We've shown it's increasing on both sides, and we've labeled our axes. Okay, so that's everything that we need to do. Okay, so please, before you put any pen to paper to sketch this, have a think about what it's going to look like. Like for this left side, we said it's always increasing and it's concave down. Think about what that's going to look like. Don't just quickly rush and sketch something. And then for the right side, it's always increasing and it's concave up. What is that going to look like? Now, it doesn't have to be perfect. As long as I can see the cup shape going up and the cup shape going down, that's fine. What I don't want to see is, I've seen this many times before, students are rushing, they just do that. Right? That's increasing. It goes through the origin. That's fine. But where's the concavity? There's nothing there. So what I think you did was just draw a line. Right? Maybe you made a mistake or something, but take it slow with this. Don't just rush and quickly sketch something because you think it's right. Here, everything's mostly right. It's increasing, it's going through the origin, but there's no concavity there. Okay. So it looks completely wrong. Okay, so please keep that in mind. Don't rush and quickly draw a line. Think about what it's going to look like. Okay, but again, don't spend too much time on the sketching. If you can get these calculations done, so all of the previous work, then you should be fine. But right, don't just rush it. Okay, let's have a look at another example. Okay, so something a little bit more complicated. So we have y is equal to x cubed plus 6x squared plus 9x. Okay, just for your information, if you do get a polynomial, it will be up to fourth order. Okay, so it will be, the largest you'll get is x to the 4. Okay, so you won't have to factor anything higher than that. Okay, so quadratics and cubics, please know how to factor that. You will need to be able to do that. Okay, so we just go through the list again. We start with the x-intercepts. And if you forget what to do, just write let y equals 0, and that will help you along. So if you want to find the x-intercepts, you let y be 0. If you want to find the y-intercept, you let x be 0. If you need to write that down to remind yourself, please do so. Okay, so if y is 0, we're going to have 0 is equal to x cubed plus 6x squared plus 9x. Okay, now we've got a cubic that we need to factor. This one's not so bad because we see that each term has an x value that we can factor out. So we can do that first. So x into x squared plus 6x plus 9. Okay, so sometimes it will be a bit easier. So here we just took out an x. Sometimes it will be a bit more difficult, but you'll see what you get. Okay, now we've done this x bit, so now we're left with a quadratic. We need to factor the quadratic. So this will be x plus 3, and then we have another x plus 3. Okay. You could write this as x plus 3 all squared, or you can write it as 3 individual terms. That's up to you, right? That's your preference. But here we only get 2 solutions. From the first bit, we get x equals 0. From the second bit, we get x equals minus 3. The third bit gives us the same thing, so we don't need to write that again. So for the x-intercepts, we get 0, 0, and minus 3, 0. Please do not swap those around. Okay, so I've seen in the previous assessments when students have points, sometimes for the x-intercepts, they'll write 0 minus 3. They'll swap that. Now, that's not so bad here because you've got x equals minus 3, but when you're sketching, now the points is going to be along the y-axis. So your sketch is going to be way off. So please make sure when you find your x values, those are right, and then when you write them as points, please make sure that's also correct. Okay, you don't want to get all the values right, and then your points are flipped over. Okay, so please make sure you've got that correct order. Okay, so we've got 2 x-intercepts. What about the y-intercepts? So y-intercept, x is equal to 0, just to remind us what to do. So we can look here. If I put in x is 0, we see all of those are going to be 0, so we get y is 0. So for the y-intercept, we get 0, 0. Okay, so this is similar to what we had before. The x-intercept, one of them was 0, one of them was the origin, y-intercept was the origin, so when we're sketching this, it has to go through the origin. Okay, so that's something to note. Okay, next, intervals of increase and decrease. Okay, and again, once we have these intervals, we can find out what those turning points are all in one go. So the turning points, as well as these intervals, we can do it all at once. Okay, so y prime, we need to know what the derivative is, or we need to know what the gradient is. That's going to be 3x squared plus 12x plus 9, and we set it to 0. Right, that's the usual thing. Now, before we try and factor this, let's try simplify these coefficients. So we've got a 3, we've got a 12, we can take a factor of 3 out there, and we've got a 9, we can also take a factor of 3 out. So whenever you can simplify the coefficients, please do that. Okay, if you have large coefficients, things can go wrong. If you have nice coefficients, it's a bit easier to work with. So if we take a 3 out, we're going to get 3 in the front, x squared plus 4x plus 3. Right, that looks a whole lot better than what we had before. Okay, so now the coefficients of x squared is 1. It makes the factoring quite a bit easier to do. If the coefficients is 3, that's a bit more work. Okay, so like on this first line, if we wanted to factor this, we would need to find the factors of 27. That's a pretty long list. Here, we only need to find the factors of 3. It's a very short list. So we see this makes things a lot easier. Okay, this is easy to factor, so that's going to be x plus 3 and x plus 1. Okay, a lot easier than what we would have to do if we didn't take that factor of 3 out. Okay, this will give us 2 solutions. So x equals minus 3 for the first bit, x equals minus 1 for the second bit. So those are going to be our turning points. And in between the turning points, it's either increasing to a maximum and then decreasing, or decreasing to a minimum and then increasing. Right, we covered that before with minimum and maximum. Okay, so let's draw a number line. You don't have to draw a number line. If you know another method, that's fine. I just want to show you this one. So x equals -1, that's going to be somewhere here. X equals -3, that's going to be somewhere here. So now we look at these different intervals that it's created. So we look at values before -3, see what happens there. We look at values between -3 and -1, that's another interval. And then from -1 onwards, we look for values there. Okay, so values before -3, we can use -4, that will work. So we look back at our gradient equation there, we substitute -4 and see what we get. So the exact value doesn't matter, we're only looking for if it's positive or negative. So here we put in a -4, that's, let's say over there, we put in -4, we see what we get. Is it positive? Is it negative? In that case, it will be positive, so we can put a plus. Okay, then between -3 and -1, we can put -2. We substitute -2, we see what we get for the gradient. Is it positive? Is it negative? It's going to be negative. And then somewhere after -1, we can put in 0, for example. We see that it's going to be positive again, so we can put a plus. Okay, now we're going to read this as the plus means it's increasing. Then at -3 is a turning point. Then from -3 to -1, it's decreasing, so we write decreasing. Then -1, that's another turning point. And then after -1, it's increasing again. So that is the pattern of this function. So it's going to increase to -3, so -3 is going to be a maximum there. Then it decreases to -1, so there will be a minimum there. And then from -1 onwards, it increases again. Okay, so what are these turning points? We know the x values, there and there. What are the y values? So f of -3, that's going to be 0, you can check that. Or you can remember that this was the x-intercept. So you can do the calculation again, or you can check from before. And then f of -1, you can check that. It's going to be -4. Okay, so -3, remember this was our maximum, or local max. And this one, that's going to be our local min. Okay. Okay, so that's all we really need. Let's sketch this now. So we have x and y. Let's put in our x-intercepts and y-intercepts. We know that there's one here at -3, so -3 and 0. We've got another one here at 0, 0. Okay, so that is our x-intercept and y-intercept. Then the minimum and maximum. So we've got a local max at -3, so it's going to be something like that, okay, because it's a maximum. And then at -1, -4, we get a local min. So that's going to be somewhere here. -1, -4, it's going to be something like that. Okay, because it's a minimum, so it's going to be a little cup shape. And then we can just connect the dots. So before -3, it's increasing. From -3 to -1, it's decreasing. From -1 onwards, it's increasing. So we just keep that in our minds. Increasing, decreasing, increasing. And let's connect the dots. So it's going to be increasing, then it will be decreasing, then it will be increasing, and it does that forever onwards. Okay, and we're done. Okay, so this is all we needed for calculating this. I'll get your question now. So this is everything we really need. If you want some bonus marks for these questions, you can calculate the inflection point as well over there. Okay, it's very easy to calculate the inflection point. It's not needed for sketching because we can just connect the dots, but if you would like some bonus marks, you can do that. So inflection points, I'll give you that as a bonus mark. Okay, so in this case, it's not necessary, but we saw in the previous example, you had to calculate the inflection points. So sometimes it's compulsory to actually sketch it, other times it's just an extra bit that you need. Okay, so if it is an extra bit, you can calculate it. I can give you some marks for that. Just make sure it's labeled so I can see what you're doing. Okay, yeah, question. Sorry? Answered it already. Okay, sure. I'm too good. Okay, so again, that's just a little extra bit you can do. Okay, any other questions? Yeah. Yeah, which bit? Local max. Yeah, so the local maximum is between these two intervals. So when it's increasing and then decreasing, we call that point the local max. So if it goes from increasing to decreasing, that's the local max. And then for the local min, that's the other one here, that's when we're decreasing and then increasing. Okay, that's how we tell which one's which. Okay, yes. Sure. How far? Yeah. Oh, so that's just from setting each of these terms to 0. So here we could call this A, B, C. Sorry, C. So if we have the product of things being equal to 0, then each of them could be 0. So A, B, C equals 0. A could be 0, B could be 0, or C could be 0. So we just looked at each one individually. So for the first one, x, that could be 0. X plus 3 could be 0. So if x plus 3 is 0, we take the 3 over. So then x equals minus 3. And then for that third one, we get the same answer. So we don't need to worry about that. Yeah. So you would take each bracket, set it to equal to 0, and then solve for x. Yeah. So whatever brackets you get, you set to 0, and then solve. Okay, yeah. So the method, you can use whatever method you like. This is just something that I'm showing you, but if you know a different method for solving this, that's fine. Okay. Okay. Yeah. Yeah, so the point of inflection here, let's go back here, that will be in between the two. So if you have a local max and a local min, the points of inflection will be in the middle there.
So the question is, if I can find the local and the maximum point, there's no need to calculate.
Yeah, if you don't need to, then that's fine. Yeah. So here you could just connect the dots. I'm not too worried about that because I just want the shape of it. But in the previous question, it was compulsory to find it. So you couldn't sketch it without finding it. In this case, it's optional. Okay, so it depends on what you have. Okay, so remember this is just a rough sketch of the shape. Okay, but a quick way to find it is it's in between the two. So if it goes from max to min, there's the inflection somewhere there. Okay, any other questions before we move on? Okay, let's have a look at the next one. Okay, so we have y is equal to 8x squared minus x to the 4th. Okay, so that's the highest power that we're going to work with. Okay, so x to the 4th. Okay, so let's have a look at the x-intercepts. So again, just a reminder, x-intercepts, we let y be 0. Okay, so what do? We set y to be 0, and then we have 8x squared minus x to the 4. Now here, we need to factor this. Now this is factoring an x to the 4. That's going to be very difficult in general, but we see here that we've got an x squared common to both. So the x to the 4 may be scary, but there's some things we can do to simplify. So here 0 is equal to, we can take out an x squared first, and then we have 8 minus x squared. Okay, so now it's not so scary. Okay, so whatever equation you get, you're guaranteed to be able to factor it. So you won't get a general x to the 4 that you need to factor. There's always some trick that you can use to make it simpler. Same thing with the x cubed. Right? There's always something you can do to make it simpler than it looks. Okay, now 8 minus x squared, that's going to be a difference of squares. So we have 0 is equal to x squared, x plus 2 root 2, x minus 2 root 2. Okay, so that's just taking the roots on both sides there. Okay, now we do the same thing as before. We look at each of the brackets, set them to 0, and that will give us our x-intercepts. So this first one, x squared is 0, so that means x must be 0, which means we have the point 0, 0. Okay, that's one of our x-intercepts. We can look at the next one. X plus 2 root 2 equals 0. So x equals minus 2 root 2. So that is another intercept. Last one, x minus 2 root 2 equals 0. So x equals 2 root 2. So we have 2 root 2 and 0. Okay, so now we have 3 intercepts to worry about. Yeah.
On the top part, the x was negative, then here, when factorizes, the x becomes positive.
Yeah, okay, good point. So here, I like to write it with the x in the front there. So what I did was I took out a minus sign. So with this line, if we take out a minus sign, we could write it as 0 equals minus x squared minus 8. But then because the other side is 0, we can just multiply by minus 1. Okay. So if the left-hand side is 0, we can just swap them because the minus sign cancels with the 0. Okay. But if you do want to write it the other way, we could write it as 0 equals x squared 2 root 2 minus x 2 root 2 plus x. Sorry, plus x. You would get the same answer. Okay. So you can rearrange it if you want. You'll get the same answer either way. Okay, so this is without the taking out the minus sign. Okay, so we've got the 3 x-intercepts. Now the y-intercept. Let x be 0. And we see if we let x be 0, we get 0. So that means y is 0. So we get 0, 0. Okay, so we've got our x-intercepts, we've got our y-intercept. Now we can look for the intervals of increase and decrease, as well as the turning points. Okay, so we take the derivative, set it to 0. So y prime, we look back here, 8x squared minus 4, x to the 4, sorry. So that's going to be 16x minus 4x cubed, and that must be 0. Okay, and we need to factor, because we want to solve for x. Again, like with the previous one, it's best to divide by 4, just to make things a bit easier for ourselves. So we can take out a 4. We're left with a 4x minus x cubed is equal to 0. Now we've got the 4 there, we can just cancel it because the right-hand side is 0, so that can go away. So we're left with 4x minus x cubed is equal to 0, and this is a bit easier to work with. Now, looking at each term, we've got an x for the first one, we've got an x for the second one, we can factor out an x. Okay, so that's the first bit of factoring. Now we're left with 4 minus x squared, so now we've got another step of factoring. So this will be x, 2 minus x, 2 plus x. Okay, again, difference of squares there. Okay, so here we've got 3 values that we need to look at. So for the first one, we get x is equal to 0. 2 minus x is 0. That gives us x is equal to 2. And then 2 plus x equals 0. That gives us x is equal to minus 2. So now when we draw that line and we look for the plus and the minus, we've got 3 points separating the intervals. So we've got x. X equals minus 2 we can put here. Then there's 0 in between, and then there's 2 somewhere there. Okay, so now we've got 1, 2, 3, 4 intervals to look at. So it will be increasing and decreasing across those 4 intervals. Now we look at something before minus 2 and see what we get. So we go back here, we put in something that's smaller than minus 2, maybe minus 3, and we see, is it positive, is it negative? So we're going to get something positive. Then something between minus 2 and 0, so we can put minus 1, and we can see, is it positive, is it negative? It's going to be negative. Between 0 and 2, we can put 1. Is it positive, is it negative? In this case, it will be positive. And then something bigger than 2, you can put in 3. Again, is it positive, is it negative? It's negative. Okay. So we see we've got these 4 intervals, and what's happening on these 4 intervals? So for the first one, it's increasing. Okay, so maybe it's good to write that down so we see what to do. Then it's decreasing. Then it's increasing. And finally, it's decreasing. So that will help us with our sketching. We know, should we go up or should we go down? Now, in between these intervals, we're going to have local max or local min. If it's increasing, then decreasing, it's going to go up, then it's going to go down. So it's a local max between here. Decreasing, then increasing, that means there's a local min between those. Again, increasing, then decreasing, there's going to be a local max between those. Okay, so we got local max, local min, local max. What are those values going to be? So the first one will be at minus 2. So at x equals minus 2, we have a local max. What is the value? So we have f of minus 2. You can check that. That's going to be 16. And then at 0, what do we get? That's going to be a local min. We just go back here, we can see 0, 0. So we have a local min at that point. So local max, local min, and then f at 2, you can work that out. That's also going to be 16. That will be another local max. Okay. And then you can calculate the inflection points as well. But for this, we don't need it to get a rough sketch. Okay, so what's this going to look like? We have x and y. Let's put in our intercepts. So if we go right back to the top, the x-intercepts, they were 0, minus 2 root 2, and 2 root 2. Okay, so we can put those in. So somewhere over here, again, doesn't need to be exact, but roughly correct. This will be minus 2 root 2 and 0. Then we had another one at the origin at 0, 0. And then somewhere over here, we have 2 root 2, 2 root 2 and 0. And then the y-intercept, if you forgot what that was, let's go up and check. So the y-intercept was 0, 0. We included that already, so that's fine. Okay, intervals of increase and decrease, that's where we now draw those lines. Okay, so it's going to be increasing to a local max. That local max is at -2 and 16. So that's going to be somewhere here. We know that's a local max, so it looks something like that. Then 0, 0, that was the local min, it will be something like that. And then at 2, 16, that will be another local max somewhere here. Okay, now we can just connect the dots. So it's increasing all the way up to this -2, so it must be something like this. Then from -2 to 0, it's decreasing, so it's going to turn around and go down, turn around and go up, turn around and go back down. Okay, so it's going to be something like that. Okay, and then the inflection points, if you were to calculate them, they would be somewhere here, and then somewhere here, because that's when it changes from concave down to concave up. So there's concave down, there's concave up, and then concave up to concave down. So you can put those inflection points as well. Okay, like that. So then there and there, those will be our 2 inflection points. Okay, and then they will lie somewhere between the local max and local min. You'll have an inflection point there, and then somewhere between this local min and then this local max here, you'll have another one over there. Okay, so some easy bonus marks for that. All right, any questions so far? Okay, so this was on sketching polynomials. So reminder, it will be up to x to the 4. So you should be able to sketch any polynomial up to that power. So you won't have any x to the 5 and so on. Okay, let's have a look at the next one. So just note, if it is x to the 5, then there's some trick that you can do to do it easily. Okay. So in the tutorial, there's a x to the 5 problem. There's a little trick to make it a bit easier to do. Okay. But I won't expect you to know that for the test. Okay, next one. So we're going to move on from polynomials to rational functions. So a rational function is similar to like a rational number, where you've got the numerator and denominator, except in this case, the top and the bottom will now be polynomials. So we're going to have something like this. So x squared minus 4 divided by x squared minus 2x. Okay, so we call this a rational function, where we've got a polynomial at the top and a polynomial at the bottom. Okay, and we would like to sketch this. Now, just note with these rational functions, this denominator part here, sometimes that can be 0. Right, so x squared minus 2x, there's some values of x where that's 0. And if we're dividing by 0, we're going to end up with a vertical asymptote. So just a note. Okay, so sometimes this can be 0. Then we have a vertical asymptote. Okay, so for polynomials, we don't have to worry about asymptotes. For rational functions, we do. So you will have vertical asymptotes because of this denominator. You must also look out for horizontal asymptotes. Okay, but this is just one of them that we're going to be looking at now. Okay, so x squared minus 2x, that's going to give us an asymptote there. Now, something to notice with this is that when x is equal to 2, the numerator is 0, the denominator is also 0. So we have 0 over 0. That's an indeterminate form. In other words, this function here, this rational function, is not continuous at x equals 2. So we have a problem there. Okay, so please make sure you can spot that. So you need to be able to spot when these rational functions are continuous or not. Okay, so you've done continuity before? Yes, okay. So here, this is not continuous at x equals 2. But it's a removable discontinuity. So we'll see that this top part and this bottom part, we have that problem at x equals 2, but it's a removable problem. So first we're going to remove it, and then we're going to do the problem. Okay, so let's write it out. So x squared minus 4 over x squared minus 2x. Now, you can do this without knowing that there was the problem, but in your calculation, you'll see up, there's always a problem when x is equal to 2. Okay, so if you don't notice this at first, you will see it in the calculation. But if you do notice it at the beginning, it does help a lot. Okay, so let's factor the top. That's going to be x plus 2, x minus 2. And we can factor the bottom. We can take out an x, and we're left with an x minus 2. And we see that at the top and at the bottom, we've got our problem term. When x is equal to 2, this top bracket over here, this bit there, that's going to be 0. This bottom part, that's also going to be 0. That's what's giving us that indeterminate form. So let's just remove it. Okay, so we get rid of the top, we get rid of the bottom there, and we're left with x plus 2 over x, which is a lot nicer to work with. Okay, so sometimes you can simplify these, sometimes you can't. It just depends on what question you're given. In this case, we could simplify the top and the bottom, so we get something that's a lot easier to work with. Okay, so instead of that previous function, let's sketch this new function without that discontinuity. Okay, now we go through the list again. We look for intercepts, x-intercepts, y-intercepts, turning points, and so on. Okay, so x-intercepts. Okay, we let y equal 0. So we have 0 is equal to x plus 2 over x. Now this denominator, that can't be 0, so we just cancel that. And we're left with x plus 2 equals 0. This gives us x equals minus 2. So we have an x-intercept at minus 2, 0. Okay, what about y-intercept? If we let x be equal to 0, then we're going to have 2 divided by 0. That's going to be infinity. So we don't have a y-intercept. Instead, we have a vertical asymptote. So we have a vertical asymptote at x equals 0. Okay, so no y-intercept. We have that asymptote there. Okay, what about a horizontal asymptote? Now, to find the horizontal asymptote, you can do it 2 ways. You can do it by inspection. So if you've done enough homework problems, you could probably just see what it should be, or you can do the calculation and work it out. Okay, so to work it out, remember with the horizontal asymptote, that's going to be a horizontal line that the function approaches at infinity and at minus infinity, right? Like with that hyperbola, right? So if we have a look at that, there and there, we see that the function approaches 0 going to x is equal to infinity and minus infinity. So to find those asymptotes, we can then take the limit and see what we get. So we can take the limit as x goes to infinity of this, x plus 2 over x. Okay, this is an indeterminate form, type infinity over infinity. You can use L'Hopital's rule. This just gives us 1. Right, taking the derivative on the top and the bottom, that gives us 1 over 1, that's just 1. Okay, quite simple. Again, please, if you struggling with that L'Hopital's rule, please ask for help. You will be needing it for the section. And then if we take it to minus infinity, we get the same thing. So we have one horizontal asymptote at y equals 1. Okay, that's all we need for sketching this. Okay, so we put in our axes, x and y. We have a vertical asymptote at x equals 0, but that's the y-axis. So just to illustrate that, let me highlight that. So this vertical axis, x equals 0, that is also the asymptote. Okay, then we have another asymptote at y equals 1. Okay, y equals 1. What else do we know? We know that there's an x-intercept at minus 2, 0, so we can put that there. Okay, okay, so that's it for now. So let's fill in what we need. Now we know that the function is always approaching this asymptote. So from minus infinity, it's like just touching the asymptote. So it's going to go like this, through the intercept, and then the y-axis is also an asymptote. So it needs to go along there as well. So it looks like that. Okay, this asymptote continues down. Okay, so whenever you have two asymptotes intersecting like this, then we know that it goes from the one asymptote and then it must go along the other asymptote, right, like the hyperbola. Then for the top one, we have the same thing. It must go along the vertical asymptote and end up going along the horizontal asymptote. Okay, but we're not done yet. Remember that problem point, the one at 2, we need to include that. Remember that was a discontinuity there. So at 2, 2, we have an open circle 2, 2, because we don't include that point. Okay, remember that was that indeterminate form there. So since it's not continuous at that point, we have an open circle there. Okay, please make sure you include that. That's part of the sketching. So this open circle means we don't include the point because of that discontinuity. Okay, so we need an open circle to exclude that point. Because of the discontinuity. Okay, so please make sure you include any discontinuities like that. Okay, we'll have a look at one more. Okay, so y is equal to x squared over x squared plus 9. Okay, so here again, we've got a rational function, the top part and the bottom part. We need to try and sketch this. Okay, so let's first look at the horizontal asymptotes. So remember, you can do this in any order, as long as you have all the information at the end. So let's look at the horizontal asymptotes first. Okay, so here we want to take the limit as x goes to infinity of x squared over x squared plus 9. Okay, so we've got that L'Hopital's rule. So you can use L'Hopital's rule if you want, or another method. At the top and the bottom, we can factor out an x squared. So we can write this as the limit as x goes to infinity, x squared times 1. Over x squared 1 plus 9 over x squared. Okay, so we've just factored that out. Okay, so here we can cancel the x squared at the top and the bottom. So we're left with the limit as x goes to infinity of 1 over 1 plus 9 over x squared. Okay, now if we take the limit as x goes to infinity, we see that this 9 over x squared, that's going to go to 0. Right, because the bottom part goes bigger and bigger, so the fraction gets smaller and smaller. This ends up going to 0. So we just have 1 over 1, so we have 1. Okay, you can also try that out with L'Hopital's rule. You'll get the same answer. Okay, so we've got a horizontal asymptote at y equals 1. And then we can calculate the x-intercepts and y-intercepts. Okay, so x-intercepts, we let y be 0. Okay, what do we get? If we let y be 0, the only solution we get is x is 0. Okay, what about the y-intercepts? So here we let x be 0. If we let x be 0, we're going to get 0 over 9, that's 0, so y is also 0. Okay, so the x-intercept is the same as the y-intercept, and we have that at the origin there. Next, intervals of increase and decrease, and local max and min. Okay, so we need to calculate the gradient, or the first derivative. So that's going to be y prime. We see we've got a quotient of things, so we use the quotient rule. Please do not differentiate just the top and the bottom. Okay, that's wrong. I've seen quite a few students doing that. Please use the quotient rule. Okay, so y prime, that's going to be 2x, x squared plus 9, minus 2x, x squared. Okay, all over x squared plus 9, and then we square all of that. Okay, so simplifying this, we're going to get a 2x cubed minus a 2x cubed, so that goes away. Then we get a 2x times 9, so that will be an 18x. Okay, so now notice that this bottom part is always positive, right? X squared plus 9, all of it squared, it's always positive. So if we're looking at where this is positive or negative, it's going to be determined by this top part. So it's going to be decreasing when x is less than 0, because when x is less than 0, y prime is less than 0, the gradient is negative, which means it's decreasing. And it's going to be increasing when x is greater than 0, because y prime is going to be greater than 0, the gradient is going to be positive, which means it's increasing. So we see that before x is 0, it's going to be sloping down. After x equals 0, it's going to be going up again. Which means at x equals 0, we're going to have a local min, because it's going to be decreasing down to the local min and then increasing again. Okay, so that's everything we need to sketch this. Okay, so here we have x and y. Let's put y equals 1, that's our asymptote. Okay, notice we don't have any vertical asymptotes in this case, because this bottom part, x squared plus 9, is always positive. Right, so it's never going to be 0, so we don't have to worry about vertical asymptotes. Okay, we just have a horizontal asymptote. So sometimes you'll have both, sometimes you'll just have one. It depends on what you get. Okay, and then at the origin here, we have our local min. Now it's going to be decreasing down to this point and then increasing. Now a function can never cross an asymptote. So if it's going to be decreasing down to the origin, it can never cross the asymptote, so it must be below the asymptote. So it must be like this, down to the bottom there. Right, that's the only thing it can be, because it can never cross the asymptote. Then we've got a local min there, and then it's going to go back up like that. Again, it can never cross the asymptote, so it must just go like that. Okay, and then it will carry on like that there. Okay, and then at the bottom there, we've got our local min, like we said earlier. Okay. And then you can also calculate the inflection points if you want, but that's not needed here. Okay, any questions on this? Okay, so just to summarize, you'll need to know how to sketch the polynomials up to order 4. Okay, sometimes it will be order 5, but then there will be a trick to do that. Just look at the tutorial. For the rational functions, you'll have the same thing, a polynomial divided by another polynomial. In that case, you can have vertical asymptotes or horizontal asymptotes. In this case, we only had a horizontal asymptote, so it might not always be both. Okay, and then there's that list of 5 things. You might need more than those 5 things. You might need less than those 5 things. Okay. Yeah, you had a question?
So I was wondering if the point 3 and negative 3, will the graph be continuous or?
It will be continuous there. So over here and over here, it will be continuous because if I put in 3 or negative 3, then this bottom part will just be 18. And then the top part will be 9. So at minus 3 and 3, you just get a value of, will be a half. Okay, so you don't have to worry about any limiting behavior or anything there. Okay, so there's no discontinuities with this. Okay, but there is the asymptote. Okay, any other questions? Okay, so like I was saying, those 5 things, you might need less than those 5 things, you might need more. It depends on what you have. Okay, let me give you some homework problems. Okay, and for those of you that didn't check your email, remember from now on these homework problems will be compulsory. You will need to write them out and hand them to me for marking. Okay, so the marks for the homework, they won't be any formative or summative, but you will get a mark for the submission. Okay, so for each homework problems, you either get a 1 if you submit or a 0 if you don't submit. If you would like me to go through the homework with you, you can come to my office with your submission and we can go through it. Okay, or you can just look at the solutions. For these homework problems, it will be due on Monday by the end of the lecture period. Okay, so our Monday lecture period, by the end of that period, I should have everyone's homework problems. Okay, and that will be from now till the end of the semester. Okay, so let's just give you a few to do. So we have y is equal to x cubed minus 2x plus 1. Y equals x to the 4 plus 3x cubed plus x. And y equals x squared plus 2x plus 1 over x plus 1. Okay, so these 3, they'll be due in full by the end of the lecture on Monday. So you don't have to hand it in, like at the end of the due date, you can hand it in to me end of today, you can do it tomorrow, anytime up until the end. Okay, so if you want to see me after the tutorial tomorrow and hand it in, if you have questions you want me to go through, that's fine as well. Okay. Okay, so I will be in my office most of the time. If you have questions, please come and ask. Okay. So the same goes for the tutorials. So the tutorials will also be compulsory. You'll need to hand that in, not to me, but to the tutors. Okay, so by the end of the tutorial period, you'll need to hand that in. That won't be for this tutorial. It will start from next week. Okay, so this tutorial, you don't have to worry about handing in. From next week, you will need to hand it in, and it will, the submission will then count. Okay, same as the homework. So you don't need to get everything correct. You'll get a 1 if you submit the work. You'll get a 0 if you don't submit the work. And then that, adding all of that up, that will count as a formative mark. Okay, any questions on that? Okay, and then just one last reminder for the test tomorrow. So it's not a practice test, that's going to be the full test. We will write as soon as you get to the tutorial, so we won't have that little bit in the beginning. So you'll write the test, and then at the end of the test you can go, or you can stay if you have any questions. But we won't have a tutorial. Okay, so most of the tutorial questions we have done today. The rest of it will be uploaded. Okay, but if you do have any questions, you can stay afterwards, or you can see me in my office as well. Okay, any questions before we go? Okay, and the point system for the homework still holds. Okay, so if you do submit this first, you will get the points as usual. But now everyone needs to submit as well. Okay, so I'll see you for the test tomorrow.